Okay, I guess I'll begin. I don't think more people are going to join. Right, so like the problem we're dealing with over here is basically multi-label classification, where it's basically when you have like a classifier, when you're training it for a set of L labels and your output is going to be a subset of those labels. How do you model given a particular input or an instance, how do you model that input to a subset of those labels? You have to define a probabilistic or a mathematical framework for that. One, to maximize the subset accuracy, or like F measure and all of those metrics. And the other one is how do you evaluate the rankings of those labels uh, in terms of basically in a probabilistic manner. Like so very basic. So ultimately, what we're doing, like the most naive approach, is use a binary classifier for each label and like independent binary classifiers for each label, and you train them individually, and you predict for each label essentially. But what this happens, what this is basically ignoring is, so for example, when you're training a multi-label classification problem for say text generation, or for some particular instance where like the two observations are related to each other, this kind of naive approach will ignore those interdependencies, and we lose some valuable information along the way. So what we do is basically to model these dependencies, we decompose the joint probability into a product of like the individual probabilities, basically in a sequence. So it's going to be your joint probability is going to be decomposed into your the product of probabilities of the first label into the conditional probability in for the second label, and so on and so forth. So it's basically going to be propagated. And like the conditional probability for this example, they've given a softmax function on the output for the for the function. And yeah, so one of the earliest methods to model those dependencies was using something called a probabilistic classifier chain, which is basically an ensemble of classifiers. So your joint probability, you're basically decomposing that into several functions. So it's going to be a product of these functions, where these functions are basically your classifier. It could be any parameterized function of your input giving you the output. So F1 or Fi basically. And it's basically, so the next label is generated. So the classifiers are trained individually, and the next label is generated based on the previous labels generated. So like I said, so it's basically dependent on the previous values. And but the problem with this is since it's an ensemble, the errors, the variance and the errors are going to be propagated as you go forward. So if you start with say an arbitrary label order, and you try to predict, and you basically take some permutations of it for the ranking, because like you have no metric of how important the ranking is. So you can either generate a random or fixed arbitrary ranking, or you can say, you can sort the labels by saying, okay, the most frequent labels are going to appear first, and the less frequent ones are going to appear at the end, or vice versa. So yeah, so basically you select a fixed like an arbitrary ranking of the labels, and you train your ensemble of classifiers. But like as you go forward in the ensemble, your errors are also going to be propagated, which is going to reduce your accuracy, your subset accuracy. So then you convert this problem into a sequence problem. So your subset of labels is basically going to be treated as a sequence of outputs. So when we're dealing with these kind of problems, the best solution is an RNN. And in this paper, they've used a GRU to deal with vanishing gradients. So it's basically, we're doing the same, we're solving the same problem. We're trying to optimize, maximize the joint probability, but we're trying to reduce the error propagation caused by the chain of classifiers. So we use a neural network to do that. And basically what this neural network is doing, it's sampling the random sequence. So your sequence of labels which is generated is going to be sampled by the neural network, like by the intermediate stages of the neural network. So as it's training, it's going to sample the sequence based on what it's learned so far. And your target sequence is going to be generated accordingly. And yeah, so the assumption is, again, the independence assumption, where the joint probabilities can be reduced to a product of conditional probabilities. But in practice, we see that because of sampling, this doesn't happen. Basically, if you take two RNNs and you train them with the same training data or the same sequence, because when you're sampling from a distribution of rankings or a distribution of sequences, the output's not always going to be the same. The target values are going to be different. So this is one of the so basically this principle doesn't hold, the decomposition principle doesn't hold in practice. Another variance of the RNN which is performed well is the encoder decoder. The encoder is basically a network which captures the information of the input. So a context of the input of, for example, if you're dealing with text, it's basically a document is going to be a document is going to be a set of words. The words can be represented as vectors, say TF-IDF or word-to-vec or any kind of embedding. So your document is, say, a set of V words, your vocabularies. So it's going to be a matrix. So you're basically decomposing that matrix into a vector through a neural network. So you're basically mapping your input to an embedding or a set or a vector in a way, and your decoder basically converts that embedding or the output of the encoder into your target label sequence. So, and it's also the sequence to sequence is basically it's also called sequence to sequence. You can read about it more. I provided a reference for it if anyone wants to get into it. Yeah, so now we're going to talk about how these guys deal with the problem of basically how when you're dealing with permutations of training of your labels of your output, how do you evaluate which ranking is better, or how do you generate those kind of random sequences? So one way is when you're bootstrapping your the sequence generation with normal EM expectation maximization neural network. So you're basically training a neural network with the cross entropy loss, but your target sequences are also going to be generated by the neural network. This is done by, so you can see in this example, basically what it's going to do is it's going to start sampling your output label sequences from a distribution. Basically your conditional distribution of yi given y before I, y less than I given x, comma x. So it's going to sample your labels from that, and it's only going to keep the true positive. So in this case, you see that only if it has a true target label set of 1 to 5, it's only going to keep 2 and 1. which is going to pass to the actual, which it's going to use to train the neural network. And it's also going to append the false negative. So 4, 3, 5 are the ones which it did not sample. It's just going to append that at the end in some random order. And then it's going to train the forward. The forward pass is going to, then it's going to train the neural network based on back propagation using cross entropy loss. So basically there are two passes in this. One, the forward pass is for sampling and the forward pass for prediction. And the back prop is for the loss minimization just on the, that's for after the sampling. And the advantage of this is, one, the parameters are shared, so you don't have to use a separate set of parameters for generating the sequence, for generating dynamic sequence. And the other advantage, again, which it solves the previous problem of error propagation. But so the disadvantage of this method is it does not evaluate how good the ranking of the system is. For example, if you're using, say, the top 3, you're measuring precision for the top 3 outputs. It's not going to the model is not going to train on the rankings of the subset of the labels. So if you have 5 true labels and you only want the top 3, the model is going to be independent of these rankings. So it's not going to train your neural network based on the how good, how important or how good the ranking system is for these labels. So the solution for that is reinforcement learning. So with reinforcement learning, what it's going to do is basically trying to create some kind of feedback or a reward system for these kind of rankings to estimate basically the quality of these subsequences that have been generated, which in the terms of reinforcement learning is going to basically be the policy. Your state is corresponds to the hidden state of an RNN. So it is essentially going to be an RNN, but your goal is going to be maximizing a reward function. The most popular reinforcement learning method, again, I've added resources at the end if you want to get into the maths of it, but what we're dealing with right now is the actor critic method, which basically says that you have an expected reward for each state and you have an expected reward for an action. So you have an action reward function and you have a state reward function, and your gains for each particular action is going to be the difference of that. And you use your TD estimator or your TD error basically as an unbiased estimator to train your model with regularization and all of that. So from the slide, the trajectory, you can see your reward is basically can be broken down into your trajectory, and you calculate the reward for each step. It's okay. So like this pictorial example, your actor is basically your policy for when you decide what action it's going to take at each step in a probabilistic manner, and your value function, which is basically your the value function for an action minus your advantage function, as it's called, acts as the critic. And so basically now we found 2 methods. One of them basically improves your subset accuracy and helps you train your model based on subset accuracy, and the other one, your reinforcement learning method, helps you identify how good the generated subsequences are. It tries to model the generation of subsequences, like a ranking of subsequences. So you basically can combine both of these models and through a parameter, like your total loss is going to be the loss is going to be alpha times the loss of the active critic method plus the complement of that into the model based method. So, and then you can just share parameters for the, like, you can basically use the same network based share parameters except for the value function parameter of the reinforcement network. And and your reward function basically is going to be whatever metric you're dealing with. It could be, when you're maximizing accuracy, it could be some metric like an F1 or an F measure or true positive or something of that sort. Or if you're using ranking based measures, you can use precision or DCG, which I'll get to later. So the experiment for the neural network, so the embeddings had a dimension of 512 and each layer had 2048 activation units. The hyperparameters, they tried to set a bunch of them, like combinations of each. And the evaluation metrics I was talking about, one is you basically identify how good your prediction is, which is basically your label based or example based, where you use F measures or accuracy. And the other one is how good your generated sequences, where you use either precision or your discounted cumulative gain, which basically weighs the ranking in a way that the top value. So the first label predictor is going to have a higher weight, the second one will have a lower one, and so on and so forth. So those are the two evaluation metrics they use for to solve both of these problems basically. And the data set is from a vast collection of multi-label classifiers, classification data sets. So this is the specification of that. If anyone wants me to go slow, or if anyone has any questions, you can just ping me. But yeah. And so the output, like for label permutations, like basically if you want to see how good, so when like one of the problems it was trying to solve is, okay, when you're trying to generate your target sequences, you cannot use all your label permutations because that's going to be very computationally effective. So different label permutation strategies and how well they perform. So the method, as you can see from the image, it's basically beating the state of the art, or it's performing comparatively to the state of the art for almost all data sets. And like, so always R&D is basically when for each target sequence, for every instance, you're generating a random sequence from the subset of true values. So for example, I have 1, 2, 3, 4, 5 as my true labels. It's always going to generate a random sequence using that. So because of the randomness, it is slow to converge, but it performs well in terms of ranking features because of because of the randomization. And like, so but we also observe that the most frequent labels are also going to appear first. So there are those kind of issues in that. And there are other methods, like, so frequent to rare is going to perform better. It's going to give a higher precision because it's going to train better on the more frequent labels as compared to less frequent labels. Rare to frequent will give you a better accuracy on the rare labels. So these are all different ways of generating your sample outputs for generating from the set of permutations available. And the other one is your hyperparameter. So as from this function, you can see if you take alpha equal to 0, it's going to become a model-based network. And if you take alpha equal to 1, it's going to purely be an actor-critic method. And they basically tried various combinations of each. And so one thing they observed was if alpha becomes, if you keep alpha as 0.9 and you take a high value of gamma, which is basically a discount factor when you're for the actor critic method, it basically converges into a poor minima, which is big because of because your actor-critic method is training stochastically, so it doesn't train well for rare labels. So ideally, it's always preferred to have a combination, or to choose an alpha of say 0.6 or something, so on and so forth, for to improve convergence to a better listing minima. And complexity is like it's going to take, because one, it takes more forward pass, it requires an extra forward pass, and it requires, because of the actor-critic method, it's going to take more time for gradient update. Generally, you see that it's slightly more computationally expensive than the fixed ordering methods, where you just select the fixed policy for ordering the labels from the start and just stick to it. But it gives you a better performance, so there's that trade-off. Yeah. So finally, so this was basically has beaten or done competitively with the current state of the art in multi-label classification for both metrics. So it's basically trying to solve both problems. One, it's trying to maximize the accuracy for the multi-label classification problem. Two, it's trying to best model how those sequences are generated in terms of, it's trying to create it's trying to model how you can rank those labels, or how those sequences are generated dependent on each other. So it's this problem basically does competitively with the state of the art for both of these problems, and we can see that it performs better than using any static technique, as like frequent ordering, or just a fixed arbitrary fixed sequence. And another advantage of this was so when we're dealing with classification problems, we generally have to deal with a threshold to identify what class it belongs to. In this case, when we're dealing with ranking problems for basically top 3 precision, or the ranking scores for the top 5 ranking scores, we don't have to tune the threshold arbitrarily. The model takes care of that for us. So yeah, so these are some of the references if you want to read about the first one is the one I discussed. The second one will talk about how RNNs they are dealing with the problem. The third one deals with probabilistic classifier chains. And if you want to learn more about reinforcement learning or encoder decoder systems, you can follow any of these links. So yeah, thank you. This is how we deal with multi-label. This is how we deal with multi-label classifications for a wide range of text generation and like image classification and so on. Any questions? I think now's the time.